Hello class, this week we're going to be discussing cross-section leveling. This is very similar to both the peg test and differential leveling, which we talked about last week, and in essence is going to add one more type of data point called side shots, which you've already seen, I believe, in homework 2 from the lecture. So what is cross-section leveling used for? In general, it's used to get an understanding of how elevation changes for a route, whether that be a new route for a road, a railroad, even sewer lines or water lines, pipelines for what have you. The other reason that you would use cross-section leveling is to get an idea of the elevation over a spread area. Like a construction site, if you want to lay a foundation, typically you want your foundation to be level. So what you could do is you could use cross-section leveling to get an idea of your elevation in order to estimate how much fill we'll need for soil, how much we need to excavate. And it's used to get a general sense of how level an area is that we're going to be working at. So this week I'm going to talk about the typical circuit you would run to do cross-section leveling. And then we'll see where that takes us. So let's assume that we have this area. We'll just say it's a lot. We're going to say that we're going to build something, a house or a building of some sort. But first we have to get an idea of the elevation for this lot. So how we can do that is we can start with a temporary benchmark, which I've just assumed to be 100 feet for simplicity's sake. And the way you would get this benchmark is you would do what we talked about last week with differential leveling. You would start at a known benchmark and you'd complete a differential leveling circuit in order to establish temporary benchmarks near your construction site. I think in the example last week we discussed setting up a temporary benchmark near a tower hall. So once this is set up with a differential leveling circuit and we have a set elevation, we can then use this to go ahead and do cross-section leveling. So how that would look is like this. First, we would need to set up some sort of equipment right here, okay? Right there, right on the edge of our lot, okay? And typically right in the center. It doesn't have to be, you could start really anywhere you want, but we're gonna do it in the middle, just so I can show you side shots on both sides of the equipment. And basically what you're gonna do is you're gonna take however many turning points you need to get to this point. So we'll just assume that we needed one turning point, and we'll put it like right here, okay? And we'll say, hey, we had to do one back sight here to there. We did a front sight, okay? So you would record that in your data table, the back sight and the front sight. And then we move our equipment and we once again do a back sight. Remember, the way to tell if it's a back sight or front sight is which direction in the circuit are you going, okay? So using this information, we can get an elevation for this point. And then we'll take that elevation, add the back sight, and we have an elevation of our equipment right here. Okay. Now, typically in a differential leveling circuit, we would just continue on with the foresight, and we'd keep going like we did. However, for cross-section leveling, it introduces the idea of side shots. And what a side shot is basically what it sounds like. Rather than moving forward in our circuit, we're going to take looks at the side or at some angle not along our path, in order to get a grid-like system of data points to establish elevations over this area, okay? So we have the equipment set up here and we have an HI. So what we would do then is, depending on how accurate you needed this leveling survey to be, you would do side shots of a set distance. And we'll say this week 5 feet, okay? So over this way, we set up 5 feet over here. We stand our Philly rod up, and we take a side shot, which I'm going to put just to the side here, just so we can kind of see it, right? Now, that side shot we would record in our data table, and the elevation at that side shot is simply the height of instrument minus the side shot. And that gets you the elevation for that side shot. Just like if we were to take height of instrument and subtract the foresight, that gets us the elevation of a turning point. Subtracting the side shot gets us the elevation of that side shot. So it's the same process data analysis wise. It's just that rather than moving forward in a circuit, we're taking side shots. So once you've got that one, you would not move the equipment, but you would go ahead and go another 5 feet out, and you would do another side in down to that one. Okay? Same thing as before. We'll go ahead and label for simplicity's sake side shot 1, side shot 2. Okay? Same thing though, our equipment is in the same place. We take a side shot, another set distance forward, and then from there we use the same equation to get our elevation at that side shot. Okay? We do it a third time, or however many times it takes to cover our area, so we'll call this side shot 3. Okay? And once again we do another side shot. Okay? So as you can see, for these 3 side shots, we didn't have to move the equipment. We didn't have to move the auto level, I should say. The Philly rod is obviously moving to each side shot. Okay? But that's why it's a side shot. Our equipment here doesn't move. These are simply sights we're doing without equipment movement. Okay? You could do the exact same thing you did here on the top side. So you'd have your side shot 4, side shot 5, and we'll say side shot 6. Okay? And you'd once again do side shots, sight in your Philly rod, and then in doing so, subtract from the height of instrument to get all those elevations. So then you'll have 6 elevations in a line. Okay? If we extend this idea all the way down, you can see how we could get elevations in a massive grid-like area, and then we can use that either in AutoCAD, Excel, or any other program of your choosing to establish a topographic map. We could use it to simply establish elevation changes throughout this, and then we can use that information to either estimate fill amounts, excavation amounts, or just get a general feel of what the lay of the land is. Okay, so if we want to move forward and we want to get a grid-like system, we got to move our equipment now. So now we do a new turning point. Once again, the distance of this depends on how accurate you need this and how small your grid segments are. I said assume a segment space of like 5 feet here, right? So you could do the same thing here, or you could do 10 feet, whatever you need. So we're gonna just say we have a turning point here. I didn't label this earlier, so we'll label this turning point 1. We'll label this here turning point 2. Okay? Once we establish that, we once again take a front sight. Remember, this is a front sight because now we're planning on moving forward. So it's a front sight, or foresight, I mean. Okay? So once we have that in, we have our new elevation for our turning point, which we established how to do last week. We then move our equipment forward. We back sight in. And using the elevation of TP2 plus the back sight, we now have a new HI. Okay? Now we repeat the same process. 5 feet out, 5 feet out. We've got side shot, I think this is 7, side shot 8, and side shot 9. We sight in all those. We sight those in. We go to the other side. We sight those in. We end up with more data points. And you can see now how this is going to end up being a massive grid all the way through this area. So once we get those, we would once again do another turning point. We'd set up our equipment again. You know, we do our foresight before moving our equipment. We do our back sight after we've done that. And we keep going. And you can see that by the time we finish, we're going to have elevation points for every turning point in the middle, as well as a grid-like set of points. at whatever spacing we need. Okay? Whatever spacing we need, we can do. The more accurate you need it, the more spots you're going to have to do, and the smaller these distances are going to be. Okay? So I believe the example I posted in the lab only shows one side shot on each side. It just shows the one. But note that you can do as many as you want. Okay? Because the math still works the same either way. It's always going to be the height of the instrument that you recorded that side shot from minus the side shot height, and that's going to give you all these elevations. Okay? Once you complete your grid set of side shots, you have to do the same thing we did last week. We have to be able to verify that our elevations are correct. So we're going to close this circuit. Now in the end, we end up over here. Okay. Now how you get back doesn't matter. It doesn't matter how you get back. I would say typically we want to try to move around our construction areas, but we don't necessarily need to do that. All that's important right here is that we complete our circuit. So I'm just going to complete the circuit going around this. So we would sight in here. We would do another turning point here. We would foresight in, back sight. Okay. And then we'll do one more turning point right here. Set up our equipment. And then for our last foresight, we're going to foresight back into our benchmark as we started with. Okay. Now, just like last week, if you finish a circuit, you need to verify that your circuit measurements come out okay and that we haven't made any egregious errors. So you would once again, once you have finished your circuit, you would do two things. A, compare the first height and first elevation and last elevation, and hope that those are within your range of error. So I think we established last week that typically in our labs we like to have an error of less than 0.1 feet. Okay, but that once again depends on what kind of work we're doing, what that error is. Okay, so we would do that. Secondly, we would do a page check again. And remember what our page check definition was. Our page check definition was sum of back sights minus sum of foresights, absolute value, has to equal our elevation start minus elevation finish, absolute value. Okay? Note the importance of these variables here. Side shot is not included in here. Okay? It's only back sights and foresights. Okay? Because that's where our actual travel path was along, the back sights and the foresights. We did not travel along these side shots. So that's not included in this page check. And that's one of the easiest things to mess up, is accidentally recording a back sight, foresight, or side shot as a different kind of shot, and then your elevations are off. Okay? So setting up this table is very important, and I'd like you to take a look at the both Lab 3 and Lab 4 spreadsheets to see an idea of how to set this data up. The Lab 3 spreadsheet, you can see a compact version, and then you can see a less compact version, something that I prefer because it makes it easier for me to see what all these measurements go to. Okay? If you're running low on space though, and you're very confident in your ability to understand, you can use that compact space. For Lab 4, I went ahead and used the expanded version just to make it simpler, because once you start adding in side shots and you've got, back sights, foresights, and side shots, it can get really confusing really quickly if you don't have your table set up in an organized manner. Okay? And as a reminder, if you need help setting up a table, or you need help having one of those Excel tables explained, please shoot me an email, shoot me a message. We'll schedule a time. I've already scheduled a time with several people to discuss the homework 2 table that you guys filled out, as well as certain elements from these labs. Okay. That's all for cross-section leveling though. It's very similar to differential leveling, with one added focus of we're going to start doing side shots. I hope at some point to have some help and possibly set up with Professor Kusha a time for us to go out and record a video of us actually using this equipment and getting data so you can get a better sense of exactly what's going on in this process. And once we have that video, we'll hopefully let you know when it's going to be posted, and we'll post it as soon as we have it. Otherwise, remember Tuesday office hours. If you happen to join into an office hour and I'm not there to let you in, please send me a message or an email. Sometimes when I'm doing other work at my computer, I simply don't see it. So just, get a hold of me any way you can. Otherwise, have a great week.